Okay, so now we're in chapter 13, which is the lipid chapter of this course that is found within the biochemistry segment of this course. And hopefully you've had a chance to read the sections that were designated for this unit. So a lipid, as you already read, is a compound isolated from the body tissues that is more soluble in organic solvents than it is in water. Okay, it's kind of a funny definition for a class of biomolecules, but it is what it is. They are not soluble in water, generally speaking. Okay, so they're going to clump up in the presence of water unless there's something to help make it more soluble. There's two major categories: fatty acid containing molecules and the steroids. And this diagram was constructed to help y'all, so use this as a map to navigate through this chapter, because otherwise I think it's really tough to really understand what's going on. So here's what we're talking about is lipids. That's the focus of this chapter. And you can either have fatty acid containing lipids or steroids. And we're going to spend the majority of our time in this section because obviously it encompasses a lot more than the steroids, which will just be a few slides there at the end of chapter 13. Okay, so anyways, let's go on to fatty acids. You're going to want to brush up on your organic chemistry before going forward with this discussion. So there is a fatty acid containing, I guess you can call branch of lipids, and we're going to see what those are now. So fatty acids, they have a carboxylic acid head group. Remember, carboxylic acids look like this. And this is why knowing the functional groups was so important there in the organic chapter of this course. They tend to be hydrophilic. Now, hydro means water. Philic means loving. Okay? And so this portion of the fatty acid really interacts well with water. Okay? But this part right here of the carboxylic acid is going to be the long, unbranched carbon chain tail, which is hydrophobic. Okay? And so what you have is a hydrophobic tail, which is a hydrocarbon chain, typically even in number, that is 12 to 20 carbons in length. And then you have a hydrophilic, water-loving head group. Now, hydrophobic means scared of water or water-fearing. And then here's a definition I want you to know for this chapter is essential fatty acids. Essential fatty acids are the fatty acids that must be obtained from the diet because it cannot be synthesized by the human body. And so it's essential because you need it from another place. In contrast, there's non-essential, which your body can actually make it on its own or synthesize it on its own. What we're going to be looking at is the structure of fatty acids. Now, what's shown here is a saturated fatty acid. You know from the organic chapter of this book that saturated just means that there's no double or triple bonds. I'm trying to zoom in, but it's kind of a small image. But just know that this part of the molecule is saturated, therefore there's no double bonds. And here is your, and here is your hydrophilic carboxylic acid head. Okay. Then you have monounsaturated, which kind of converts it from a linear-looking fatty acid to one with one kink in the chain, okay? And that kink is due to the presence of a double bond, CC double bond right there. Okay, so you still have this as the R group, except for that R group, that being an even number, 12 to 20 carbons in length, hydrophobic. It still has that hydrophilic head group, the carboxylic acid. The only difference between the saturated and the monounsaturated version, one is mono, so one unsaturation is the presence of a double bond, or CC double bond, or an alkene, if you will. And then polyunsaturated just means more than 1 degree of unsaturation. So what you're going to find is this is your R group, this is your R group, and they're 12 to 20 carbons long. It's even number typically. You have your hydrophilic carboxylic acid head, but this time you have more than one CC double bond. And the idea being anything more than mono, okay? So 2, 3, 4, 12. Doesn't matter as long as there's more than one CC double bond. And as you see, it really changes the shape of the fatty acid whenever you consider the degrees of unsaturation. In the saturated version, what you see is that it's kind of a straight chain. And the monounsaturated, what you see is that there's like one kink, and so it kind of has a little bend to it. And then whenever you get to polyunsaturated, notice that it almost looks like a candy cane. It's so bent. And so that's one thing I want to let you know, that shape is important whenever you consider these things. Saturated fatty acids contain only carbon-carbon single bonds, so they stack on top of each other. And as I said, that's very important. Why do they stack on top of each other? Well, think of a mason laying down bricks, okay? Whenever things are flat, it's much easier to lay down one on top of another. And this can actually cause clogging to your arteries because it can stack so well. And the reason it stacks so well is because of this nice flat structure. So I am here to tell you that it's not very, saturated fatty acids are bad for you because of this. Okay, the stacking can cause them to clump up and block blood vessels, which can cause heart attacks. And you'll find a lot of saturated fatty acids in fatty beef, butter. We all love our butter, don't we? Lard, cheese, and actually coconut oil, which is an interesting one because there's been a large push to say that this is the new magic oil and we should just eat it on up. Well, actually, it's not as great for you as people may think, okay? So just to reiterate what a fatty acid is, here's your carboxylic acid head group, and the carboxylic acid, is hydrophilic, so it likes water, and then this is hydrophobic, hydrocarbon chain, and notice that there's no CC double bonds within that, so this would just be called a saturated fatty acid. But in contrast, here's your monounsaturated, and what they have is at least one CC double bond, and it's in the cis conformation. Okay, now, monounsaturated fatty acids are pretty good for you, actually. They help to lower cholesterol. The kink in the chain makes them not able to stack on top of each other, so it's not as risky to eat this stuff because you're not prone to heart attack due to stacking, okay? And so these are the type of foods you do want to eat because they do contain monounsaturated fatty acids. Olive oil, sesame oil, avocados, and nuts. And so here's your fatty acid, carboxylic acid, hydrophilic, hydrocarbon chain tail, 12 to 20 carbons long, typically even in number. And there is your monounsaturation in the cis conformation, because if you were to divide that double bond in half, there are your groups there on the same side. Now, I do need to take a detour and tell you there are such things as trans fats. Obviously, you've heard about those, and they're incredibly bad for you. They're known to stack on top of each other, unlike the cis conformation. Those tend to be synthesized by scientists, okay? So what we're talking about in this class is more naturally occurring items. The cis form is the naturally occurring one. You may wonder why they want to transform it into trans, and that's because it's more storable, okay? Turns out that a lot of your oils that are good for you, with the monounsaturation or the polyunsaturation, they go rancid rather quickly, and so that's why you might see them in dark-coated bottles or dark green glass or plastic. It's to help preserve them longer, but ultimately saturated and your trans fats last longer, but they're the worst for you, so there's always a payoff. Here's polyunsaturated, have more than one CC double bond and cis conformations. That's talking to alkene geometry. They help to lower cholesterol as well, and these are the foods you really want to stack up on whenever you think about eating healthy, okay? Walnuts, salmon, flax seeds, and sunflower seeds. The double bonds are unstable and can be oxidized, thus making the oil or the fatty acid rancid. Scientists are trying to counteract that, but it's hard. Some are trying to use antioxidants to stop the process, but time will tell how successful scientists are. But again, here's your R group. Notice that here's your unsaturations. So that is polyunsaturated. There's your hydrophobic tail. And here's your hydrophilic carboxylic acid head group. Okay, don't memorize this table, but it's just interesting if you want to consult it for nutrition and what you ought to be eating. Boiling point trends, super important. As the number of carbons in chain increases, the melting point increases. And that's the same trend you saw with the alkanes and the alkenes and the alkyne boiling point trends. The longer the chain, the higher the melting point. Saturated fatty acids have a higher melting point than unsaturated fatty acids with similar chain lengths. Now, that might be a little challenging, but think about it this way. Whenever you have olive oil, let's say, you know that is unsaturated fatty acid. And then you have butter, which contains a lot of saturated fatty acids. Now, at room temperature, the olive oil is going to be a liquid, right? And at room temperature, the butter is going to be a solid. And so just think about it that way, okay? Butter's full of saturated fats and it's solid. What that means is that it has a higher melting point. The olive oil is a liquid at room temperature, meaning it has a lower melting point because it's already melted at room temperature. So you may want to consider it that way. The reasoning behind it is because the polyunsaturated and monounsaturated fats have a difficult time stacking on top of each other. And so it's easier to break up those intermolecular forces holding them together in a solid conformation or solid state. Therefore, just a little bit of energy, like room temperature, is enough to melt it and make it a liquid. Okay. Whereas the saturated fatty acids are stacked like bricks on a house, and it's going to take a lot more heat or energy to break those interactions. It's going to be those dispersion or London forces, and thus they're going to have a higher likelihood to be solid at room temperature because they're so stacked one on top of another and unlikely, without a whole lot of energy, to break up that interaction. Okay. And also, as the number of double bonds increases, the melting point decreases because you get more kinks in the chain. Thus, it's harder to stack on top of each other. Okay, here's some boiling point practice. Hopefully you see that. When you go from 8 carbons to 10 to 12 of similar species, the boiling point is increasing. Whenever you go from saturated to monounsaturated to polyunsaturated, it's actually increasing that way, or you can think of it as, I like to think of it actually as decreasing boiling points as you increase the unsaturation. Okay, that is all for today. Hope you enjoyed that.